Alright, hi everyone, welcome to my YouTube channel, City of Electrons. So in this video, we are going to work on this. We take an assumption, let's just consider that as an example of the relationship between electric and magnetic field. So let's just see how they relate using this example. So assuming an electric field E, so an electric field E, this is the electric field. Note, assume. Okay, so this is, so if you are wondering, okay, how do we get this number, this expression? Assume. Okay, we assume, like this is the example, this is the starting point. If you have this as the electric field to be in the positive x direction, so this is the electric field in the x direction, but it has what? A z component. Okay, so in the x direction, look at it, x direction, but it has what? Z component. What does that mean? Now that is, E is in the what? X direction with Z component, meaning E oscillates in the X direction and propagates in the Z direction. Look at it here. So you can see E is moving in the X direction. Its amplitude, or let's say, yeah, you can see that this is the X direction. Okay, but while it's moving in the X direction, okay, it propagates in the Z direction. That means it's going like this, up and this way, down. Okay, that's why we have this. Okay, now to obtain the magnetic field H of the electric field E, we consider the relationship of H and E in Faraday's law of induction. You know that in this course we are talking just about electric and magnetic field. That's electromagnetic field theory. So now we've assumed an electric field. Okay, so what about the magnetic field of that? So there is a relationship between these guys given in the Faraday's law of induction, which is this: changing magnetic field produces a changing changing electric field. That's coil. Okay, so that's what we have here. Changing magnetic field produces what? Produces an electric field. Okay, coil of an electric field. Now we call that in phasor form partial t equals j omega. So when you have this 1, 2, 3, place j omega there, and the rest remains the same. This guy remains the same. This guy, sorry, minus there. This guy becomes j omega. Mu, that's permeability. There, you, there. Okay, so we find now to get this guy, make it the subject formula. That's just divide both sides by this guy so that this guy should go under. But what is this? What is this? To find, so we find this as a coil of the electric field and substitute into equation 2. This is equation 2, and make H subject of the formula. Okay, now to get this, we use the matrix form, and I think I did this in the last video. We did this in the last video. So we just use the determinant form. Okay, like matrix. Now when you do that, you have this expression. Okay, after getting this expression, all I did at this point is just to switch this minus, multiply this guy, make this one minus. Look at it here, minus this, minus, multiply this guy, make here positive, come here, so that this sign will become what? Positive. All right, now this is the electric field we assumed, so we want it in the electric field in x direction with z components. So you look for the one that has x direction, z components, correct? X direction, not z components, so we cancel out. Are we seeing it now? So the one we have the x direction with z components. What do we have here? Ay. So we bring it out. The rest is 0. Okay, so we bring it out. That means the coil of the electric field will now give us what? This component, the x component, sorry, will now give us something in what? The y direction. Now substitute this guy into equation 3. Sorry, substitute equation 3 into equation 2, which is this. Remember now, look at it here. Okay, So we bring it here. So having this now, make this guy subject formula. This guy goes under, so you can see this guy now is moved to this other side, of course under, because we are dividing both sides by it, so we have this equals h. Now we just bring h this way and pack all these guys this way. Looking at it now, you can see that h is in which direction? Look at it, y direction. Okay, that means h equals what? Hy, meaning y direction with a what's here? Z, with z component. Okay, so we now say h is moving like this, but what? Yeah, it oscillates like this, but it propagates in the z direction. So h will be moving like this. Are we seeing it now? Now I think we don't need to do this part, but let's just, as taking the coil of the magnetic field, we confirm the direction of the electric field. So we repeat the same thing for the magnetic field, same thing we did for electric field. That is determinant method, okay, matrix. So we'll do this, we'll get that expression, and then we'll consider what? Where is this expression now? Here. We'll consider this guy. It should be hy with z components. So when you come here, you look at it, any hy z components. Okay, any other hy not z component, leave it. Okay, so the rest becomes 0 and we have this. So you can see that hy, when we take the coil of the magnetic field, we have, it shows us the direction of the what? The electric field, x direction. So it makes sense. Okay, now this confirms by this law of induction. Thus equation 1 and equation 3 will give us this diagram. So you see the electric field moving like this in this direction, but propagating in this one, so like this. And for the magnetic field, moving like this, but propagated in this direction, so we go like this. Okay, so this is the electromagnetic wave we get. All right, now and therefore the wave equation we did in previous video, when you bring that wave equation for the electric field, you see that we are considering this, right? X direction, z component. Any x direction? Yes. X direction, z component, no, cancel. X direction, z component, no, cancel. X direction, z component, yes. So you have this. Okay, yeah, of course, x direction, no, cancel. X direction, no, cancel. All right, so for x component we have just this. I mean, for electric field we have just this. I should have done this. Sorry about that. This is also squared. I hope I did this in the previous video, guys. Hey, even here too. Squared. I hope I made this correction in the last video, but please just check out the last video. If I didn't do that, just let me know and just put it there. Okay, put it there. Thank you. Now all together, so we've done that for the electric field. For the magnetic field, similar. Okay, we'll consider what? This guy, because this is what we have for the magnetic field, right? Hy is z component. Hy, no, pew. Hy, no. Hy, no. Hy, yes. Z component, no, pew. Hy, yes. Z component, nope. Hy, yes. Z component, yes. Bing. Correct. Hy, nope. Hy, no. Nope. So this is all we have. Now, note that this is, we say partial because we are considering x, y, z components. But since what we have now is just one component, so it's no longer partial, we are taking ordinary differential. So our final result will be what? D squared, that's ordinary differential now. For electric field, we have this. Magnetic field, we have this. So it's no longer partial now because we are taking one component, which is z. So we have it direct like that. Okay? So that's it. That will get what we get for the wave equation. But the solution for the wave equation, okay, we can determine that solution to the wave equations above, given that they are ordinary differential equations. So from A, all we have to do, like the approach for ordinary differential equation, Just move this guy this way, so you have this minus this equal to this. And note that the solution for differential equation, ordinary differential equation, we take it to be what? We take it to be, no, remove that x first, or let's just go with that. We take it to be what? Exponential. Okay, so you will have something here, and then let's go with this. Okay, we take it to be what? Exponential. And that should still be, let me use x there, like general form. Okay, general form, or whatever can be there. Okay, just general form. Now it's changing with respect to z, but the general form they used to put t there. That's changing with respect to time. Okay, changing with respect to time, and this m is just the root. But in our own case now, it's changing with respect to what? Z direction. So that's why I'm using z there. Okay, using z there. Then of course we'll have a constant. That constant can be 1, 2, whatever. Okay, so if you have more than one root, let me just put the order and be exponential. Okay, so this is kind of the general assumption to the solution. Okay, so I'll cancel it because I've written it before and it's down here. So this expression, this equation we have here, compare it with this form of quadratic equation, and when you compare it, what is the m squared now? Is like this guy. What is the coefficient here? 1. Then we have m, which is, this is the second derivative. The first derivative. There is no first derivative here, meaning b, the coefficient is what? 0. Then the next one, that's the ex, the constant. We have this guy, and gamma squared. So minus gamma squared, sorry. Okay, so c equals minus gamma squared. So by the time you plug in 1 into this, 0 into this, and this into this, you have this guy. And when you simplify this, m squared will be equal to, move this guy over, equal to gamma squared. And when you take the square root, square both sides, m will be equals plus or minus gamma. Now that thing I wrote down there some minutes ago, when you take this expression, you now say equal to this, which is this now. Okay, now where you have m, you put one of them. Where you have the other m, you put the other one. So one negative, one positive. Okay, thus just make this guy, instead of using a and b, let's use positive traveling wave, which is e, and a negative forward traveling wave and backward traveling wave. So use this as constants. They are just constants. Okay, they are just constants. So let's use this guy for constants traveling backwards, constant for traveling forward, constant for traveling backward. And recall that gamma, the propagation constant, equals this, attenuation constant plus what? Phase constant. Okay, so substitute in these guys into this place, you have exactly this. Okay, and all we did here is just use that index concept. If you are summing the power, it means we what? Multiply this guy. When this multiply, look, if you multiply this and this, it means you are summing the power. You will return back to this. Same thing applies here. Multiply this, you sum this guy, you return back to this. So we just expanded like this. So this is the solution for the electric field. It is similar for the magnetic field, so no need to resolve the whole thing. Just where you have E, put H. That's it. Okay, so that will be all for this video. Okay, that will be all for this video. And like, share, subscribe, comment, and I will see you in the next video. Thanks for watching, and bye for now.